Hello everyone, I'm Shresth. I'm the CEO of Pod Network, and today I will be presenting a novel approach to scaling Web3 without breaking composability. So let's get started. So blockchains today use a core primitive, which is referred to as a consensus protocol. You might have heard of proof of work, proof of stake, or some other complex consensus protocol. In essence, what it does, it orders transaction. A very nice analogy to think about consensus protocol is you take a pipe, right? And on the one side of the pipe, you have transactions in the mempool sent by the users. These are pending transactions. And then as these transactions go through the pipe, on the other side, we have transactions that are confirmed in some order. What does that mean? Every transaction has some index associated to it. It's an ordered set. That's all a consensus protocol is doing. Let's open this box. If you open the box, this is how it looks like, okay? Let's say Alice wants to say, like, transfer some USDC to Bob. The life cycle is Alice sends a transaction to a block proposer, which waits for the next block to come, and then this block proposer sends communication to all the validators. Some of these validators could be malicious, and after several rounds of voting, the transaction might get finalized and then picked up by Bob and say, okay, I received the payment. So even though this problem of ordering transaction might sound quite trivial in a centralized system, you just assign indexes, doing it on a distributed system with Byzantine nodes is extremely tricky and usually requires several rounds of communication. This is part of the reason why blockchains today are super slow, expensive, and actually do not scale more than 100 active validator set. Before I go ahead and propose the solution to this problem, let's take a step back. Let's look at how 99% of the internet looks like today, right? If you were to use, let's say, Venmo to pay, what would happen is Alice would send the transfer order to a centralized server. The centralized server might do some local validation, maybe interact with the database, and then send the receipt to Bob, and Bob would be fine, right? End-to-end, this would require less than 100 milliseconds, one network round trip, almost feel instant, right? You would not even notice that this happened, like a Google search. Now, a natural question to ask here is, can we build Web3 systems that are as fast as Google search, providing one network round trip latency? This is a very important question for us as Web3 developers and researchers to ask, because if we have even a small chance of mainstream adoption of this new internet, then we need to build this new internet almost as efficient as the existing one while still providing all of the benefits that we have, right? Decentralization, openness, etc. By the end of today's presentation, you'll realize that it is possible to build decentralized systems which can provide one network round-trip latency. And it will be very different than what we see with blockchains today. Let's get started. So I'm going to propose a dead simple solution that solves the problem of payments, right? And this will give you a taste of how the solution could look like, right? So we have the constraint that we want to finalize transaction in one network round trip. So we don't have a lot of leisure for validators to communicate among each other. So we start with a set of validators. Again, in our simple example here, we have 7 validators. We tolerate up to 1/3 malicious validator, like any stake-based network. So 2 of the validators can be malicious. You can see them with red horns. And then what Alice can do is, whenever Alice wants to write a transaction, it sends a message to all of the validators. They can perform some local validation and then send it back to Bob, who wants to read the message. So that's all the network is allowed to do, right? Alice sends to the validators do something local and send it back to Bob. This is end-to-end one network round trip. Now let's see how we can use this dead simple construction to do payments. Okay, so Alice wants to transfer 5 USDC to Bob. What Alice does is it creates this transfer order and sends it to all the validators. But it also adds a nonce to it, right? This nonce is just an index of the nth transaction. If you're familiar with Ethereum, you already know what nonce is. It's exactly the same thing. And then what validators do is they just check if the nonce is correct, is the expected nonce for Alice, check if Alice has sufficient balance, and then just sign an acknowledgement saying, this is a correct transfer order. That's it. And then once Bob receives sufficient acknowledgement from these validators, Bob can consider this transaction finalized. So here in our case, we want at least 2/3 of the validators to acknowledge that the transfer order is successful. So in our example with 7 validators, we want 5 of them. I'm representing the blue dot to represent the quorum, right? Now, the easy case where Alice is nice and is an honest user, you can see that the honest parties would sign on the acknowledgement, and because there is at least 2/3 honest parties, he will get this quorum. So the more interesting case, which people usually like to talk about on blockchains, is the case of double spending, right? What happens if Alice is malicious and tries to spend 5 USDC for both Bob and Charlie, right? It only has 5 USDC, and it's trying to transfer 5 USDC to Bob, and at the same time, it's transferring it to Charlie. Now, trivially, if it assigns, incrementing index, the first transaction would get confirmed, and the second one would, revert. But then the more interesting case is when it assigns the same index to both the transaction. In that case, what would happen is there are 2 transactions. Both of them have the quorum of 5, but we only have 7 validators. What this means is there's an intersection of 3 validators at least, right? And because we know that we only allow for up to two malicious validators, just with this simple quorum intersection argument, we can see that you cannot have 2 different transactions which can have the same index, right? We can take a pause here, and we can appreciate that just having a simple quorum already allows you to solve the double spending problem. And this is a very well-known fact in the research literature, and it has been well studied by papers like ABC, consensus number of cryptocurrency, and Fastpay. And this can already do payments which are Byzantine fault tolerant. So earlier, I described consensus as this pipe which takes transactions as input and outputs them in some globally agreed upon order, right? Now, if we look at a similar analogy for this new kind of network, right, the pipe completely shrinks because the latencies get to 1 network round trip, which is optimal, but also the pipe, the width of the pipe increases because we're using much lower bandwidth. The communication is no more quadratic, it's linear. You can finalize much more transactions, so the TPS also increases. But what do we lose, right? In the consensus approach, every transaction has a total order, while in this new approach, we don't have a total order, right? So transactions are finalized, they are part of the confirmed set, but they don't have a total order. A nice way to think about this is, in the consensus approach, transactions acquire a global lock, right? So every transaction blocks the whole system, while in this asynchronous approach, transactions are completely parallel, where they do not block each other. And this is what allows it to scale. So we already discussed how this can be used for payments, but it doesn't stop there. You can actually use it to do fast auctions, which allow you to build marketplaces for proofs, marketplaces for order flow, limit order-based DEXs, etc. You can also use it to build notarization platforms, decentralized socials, games. So a lot of applications that blockchains are used for today actually are fully commutative. And a lot of other applications, you can formulate it as commutative operations. But let us look at a simple example where things are not commutative or require ordering. So we go back to our initial example of doing payments, right? And we love the ERC20 standard. We can do transfers, but how do we build allowance, right? Let's say I have 5 USDC and I want to allow both Alice and Bob to spend this 5 USDC. What happens if they both try to spend the allowance at the same time, right? Half of the network might see Alice's transaction, other half might see Bob's transaction. They are both honest. They were just trying to honestly spend the allowance. In this case, none of the 2 transactions might get a quorum, right? More technically, whenever you have a shared state where multiple parties can write at the same time, you might end up in a deadlock because you don't know which transaction should get confirmed. And if you had some kind of ordering here, what would happen is you would confirm the first transaction that, you would order everything and then you would confirm the first transaction and then reject everything else. So let's try to fix this, right? In the payment example, one of the main tricks that allowed us to solve the double spending problem was that we asked users to assign an index to the transaction, right? This was the nonce. And that ensured that if the user assigns two different transactions with the same nonce, then the network will not finalize both of them. What if we do something similar, right? Let's introduce like a third party, we call it as an ordering gadget, right? All it's supposed to do is assign indexes, right? This could be a centralized sequencer, this could be a consensus protocol, a multisig, whatever, right? And in this case, if Alice and Bob both try to spend the allowance, only one of the two will get confirmed. The important thing to notice here is that this ordering gadget is not responsible for the safety of the protocol. It is only responsible for the liveness. What this means is, if this ordering gadget becomes malicious, goes rogue, and then tries to assign conflicting indexes, so assign same indexes to different transactions, the network ensures that the safety holds. Which means that this ordering gadget doesn't have to be very decentralized or doesn't have to have as much security as the base layer. Now this brings me to the final part of the construction. We want a base layer which is completely asynchronous, right? Which doesn't provide ordering, and it is extremely fast. It provides this optimal latency. And then, for applications that need ordering, we can allow them to build their own ordering gadgets. These could be consensus protocols, it could be centralized sequencers. And what these ordering gadgets are doing is they're just assigning indexes. So the settlement still happens on the base layer, the execution still happens on the base layer. So what this gives us is, if I'm doing a transaction between a account which lives in the base layer and an ordering gadget, because payments and transfers are still fast on the base layer, you still maintain the composability. Even transactions across the ordering gadgets are fast because the base layer provides you with this very fast commutative and transfers. But an additional point that the system provides is, because we allow applications to build their own ordering gadget, applications can control their MEV. For example, let's say you have Uniswap, right? And we have seen a huge surge of protocols deploying their own L2s to capture MEV revenue. Now, for example, Uniswap could run their own sequencer, right? Like they're doing with Unichain, but now on pod, and they could handle their MEV while still being composable with the rest of the architecture. Thanks a lot for listening. We already have a private DevNet, which has this base layer, which is extremely fast. And if these ideas resonated with you and you're excited to try it out, reach out to me, and I'm happy to give you early access to it. Thank you.
Yeah, and with